Hello everyone and welcome back to my channel Gyan Sampada. Today we are going to discuss about another type of semiconductor device, that is semiconductor lasers. As such, from the name we can understand, in this type of laser we are making use of semiconductors. So there are many types of lasers, but today we are going to discuss about semiconductor lasers because it is having widespread application. So its history, working, the principle, construction, advantages, disadvantages, as well as the application of semiconductor lasers will be discussed in today's class. So let's start our today's class by understanding the history of semiconductor lasers. As such, semiconductor lasers were invented in the year 1962 to 1963 by Robert Hall and Nick Holonyak. And this semiconductor laser is the only semiconductor device which can be used for amplification in infrared as well as optical ranges, and all others are restricted to microwave range or below. So if we need to know about its construction and condition, let us consider a gas composed of atoms and focus on two of the excited atomic energy levels 1 and 2, where N1 and N2 be the populations per unit volume of level 1 and level 2 respectively. If we consider at equilibrium, then we can understand that the ratio of their populations, that is N2 by N1 is equals to e raised to minus delta E divided by kBT, which we are calling as equation number 1 here, where delta E is equals to E2 minus E1, which is the difference in energy between the two levels, as we can observe here, and N2 is less than N1, because N2 corresponds to the higher energy state where the population is generally less than 1. So as such, we know that laser means light amplification by stimulated emission of radiation. So here we need emission. Emission means the higher energy state should have some number of electrons so that they are jumping downwards to the lower energy state, meanwhile emitting some radiation. So here we are saying stimulated emission means there has to be something which is going to bring some electrons from the lower energy state to higher energy state. That is, our aim is to make N2 comparably greater than N1 so that laser action is possible. So when an external signal of frequency omega approximately equal to delta E by H cross is passed through the gas, it is strongly absorbed. So you can observe there will be a transition from E1 to E2 due to this absorption. That is, the photons from the signal are absorbed by the electrons in the level 1, which then make the quantum transition to upper level 2 with energy E2. So as such, higher energy state is unstable. So those electrons which are in E2 will come down to the lower energy state, that is de-excitation takes place and photons are emitted. We can say their corresponding energies will be equal to H cross omega. So rough idea about the working is understood. So next, let us move on to the condition corresponding to it. So in semiconductor lasers there are two types. One is can type, another one is frame type. However, the working condition remains the same. That is, the principle of working is always remaining the same itself. So if we consider L is the length of the sample, then the intensity of the signal at the end of the sample is I is equals to I naught e raised to minus alpha L. We are considering this as equation number 2, where I naught is the initial intensity and alpha is the absorption coefficient. Simultaneously, the signal is going to help or stimulate to cause the transition from level 2 to level 1. and a photon of frequency omega approximately equal to delta E by h cross is emitted for every quantum transition. And as this process is aided by the signal, it is called as stimulated emission. So the signal of that frequency is going to act as a stimulus which is going to be responsible for the emission. That's why the name stimulated emission. And these two processes, that is absorption and stimulated emission, act competitively on the signal and both have equal probabilities of occurring. But still the net result is absorption because the level 1, which is the lower level, has the larger population when compared to the higher level. That is, N1 is going to be greater than N2 itself. Therefore, we can say that the absorption coefficient alpha is equals to B into N1 minus N2, where B is the probability constant. And as N1 is greater than N2, we can say that alpha is greater than 0. That is, absorption coefficient is going to be positive, which just means that the absorption rate is greater than the emission rate. So the basic need or the basic premise of laser device lies in the attempt to amplify the signal, and that is by making N2 greater than N1. That is, the population in the higher energy state should be greater than the population in the lower energy state, and this is achieved by inverting the population. And if N2 has to be greater than N1, which means that absorption coefficient is going to be negative. That is, alpha will be less than 0. And based on equation 2, we can say that I is equals to I naught e raised to modulus of alpha into L is going to be greater than I naught. So on inverting the population, we can say N2 is greater than N1, alpha becomes negative, but if we consider the modulus of it, then we can observe I is going to be greater than I naught. That is, the signal is amplified because there are more emitting atoms than the absorbing one. So the de-excitation is more when compared to the excitation. So by keeping all these ideas in mind, some of the points to remember or glance is, if we are considering the laser operation. In laser operation, the sample is placed in an optical cavity composed of two parallel mirrors, which we are observing here, and this is nothing but the Fabry-Perot interferometer. The main advantages of laser beam over conventional sources is they have extremely high spectral purity as well as highly directional and high intensity is obtained. And for this, the necessary condition for lasing or the laser action is mod of alpha into 2L is equals to 1, where L is the length, alpha is the absorption coefficient. How the diode is constructed can be observed in this diagram, where you can observe the carrier is injected into the depletion layer where the excitation de-excitation takes place, which is going to be responsible for the emission of laser beam. So if absorption by foreign atoms or ions etc. are included, then we can represent all these losses by another absorption coefficient, that is alpha dash, and we can denote modulus of alpha due to amplification by gain G, and thus the condition for lasing changes to G minus alpha dash is equals to 1 divided by 2 into L. So on rearranging, we will get gain G is equals to 1 by 2L plus alpha dash, which we are calling as equation number 4. So how to obtain this? That is nothing but the process of pumping. So population inversion can be achieved by pumping the gas with a strong beam of a frequency omega p is equals to E2 minus E naught divided by H cross. So I hope you remember the energy level diagram which was in the previous slide, where E0 represents the ground state, E2 represents the higher excited state. And this is the condition to excite more electrons to level 2 and thus give it a longer population than level 1. That is, N2 will become greater than N1. So by knowing all these rough details, we can understand what is the mechanism or operation of semiconductor laser. So generally we can say it is similar to the gas laser itself. So when we are going to consider a semiconductor, we know that the light beam passing through a semiconductor is going to undergo strong absorption near the band edge. That is where the absorption is going to start. That is H cross omega is equals to Eg. So for excitation, the radiation of photon should be always greater than or equal to the band gap. That is, H cross omega should be greater than or equal to Eg. Only in that case we can observe that the photon from the ground state can get excited to the higher energy state by absorbing the photon. So these details of optical absorptions in semiconductors we have already discussed in our channel. So you can go through the playlist section of optical properties in semiconductors. So there we have discussed about the band edge, fundamental absorption, each and every detail. So by keeping that in mind and about the band structure, we can clearly say that the absorption is due to the interband transition. Interband means in between the valence band and conduction band. So you can remember, interband is nothing but in between the bands, intraband is nothing but within the bands. So here it is going to be interband transition. So there again we can consider the two types of semiconductors. One is direct band gap semiconductor structure and another one is indirect band gap semiconductor. So in direct band gap we are having the top of valence band and the bottom of conduction band for the same K value, but when we have indirect band gap semiconductor structure, then the top of the valence band and the bottom of the conduction band are having different K values. So they are not one above the other. So for absorption, not just photon is required, but to gain some extra momentum, there is involvement of a phonon also. In detail, we have studied this under band structure as well as during studying absorption in case of semiconductors. So thus the amplification should be possible if the population of valence band and conduction band near the band edges could be inverted. So for that we should understand for which type of semiconductor what is the nature of bands, whether they are direct or indirect band gap semiconductors. So this especially explains the population inversion arrangement in semiconductor suitable for laser action. So suppose that the material is so heavily doped with N-type and P-type impurities that the free carriers have essentially degenerate distributions with two different quasi-Fermi levels, that is EFC and EFV, in the two bands. Then a distribution like this leads to amplification because stimulated electrons make transitions from conduction band to empty states at the top of the valence band. The empty states are nothing but the holes. And we can say the photons are emitted which are of frequency omega dash is equals to Eg by H cross in the process. And since the interband transition is quite strong, we can observe strong amplification. So that is our expectation. So above we have observed the band structure. Here we can understand this based on the energy level diagram, that is in case of heavily doped junction. So P side is little bit raised when compared to N side, and further details about energy level diagram you can refer the previous videos from the playlist of this channel. So let us move on to our main topic, that is semiconductor lasers. and the necessary condition for amplification is going to be EFC minus EFV should be greater than or equal to H cross omega, or you can say should be greater than or equal to H nu. So for H nu, if you multiply and divide by 2 pi, we can have H by 2 pi as H cross, and 2 pi nu is nothing but omega. So both are going to be similar to each other. So in case of quantum, we express with respect to generally H cross omega. So this is nothing but the energy difference, EFC minus EFV. So in this energy level diagram, we can observe when the junction is forward biased, there is certain region in space where the population inversion is accomplished. So that is evident here. So inversion region, why? Because the population inversion takes place in this depletion region. So by understanding the concept of the working and mechanism of semiconductor laser, now let us understand about the current corresponding to it. So this is how we can observe a semiconductor laser. This is the circuit symbol, that is a PN junction and emission of laser beam from the depletion layer. Then the two metal contacts, anode and cathode. So this is circuit diagram. This is how the semiconductor laser looks like, and this is when you just cut it half and you observe what all is present inside this semiconductor laser. So there is a threshold requirement for the operation of the junction laser. Let us understand about it. The population inversion should be strong enough for the gain made by the downward transitions to be larger than that of the absorption effects. So the absorptions may be like free carrier absorption, etc., such as the partial transmission incurred every time the beam is going to hit the faces of the crystal. There is a threshold carrier concentration which we denote as N, which can be related to measurable quantity, that is the junction current. And by using the equation of continuity with the diffusion equation, we have I by D approximately equal to En by tau dash. So here D is nothing but the width of the active region, that is nothing but the depletion region where inversion takes place and laser light is going to get emitted, and tau dash is the carrier recombination time. N is the threshold carrier concentration, I is the junction current. So first, laser action in semiconductor was observed in gallium arsenide junction, and the laser line lies in deep infrared region at certain wavelength of 8400 angstrom at 77 Kelvin. So this was the first observation, and it corresponds quite closely to the energy gap of the gallium arsenide. So that was the consideration or observation done which supported the condition, that is H cross omega should be greater than or equal to energy gap Eg. So as the temperature increases, the wavelength of the laser also increases, which is in agreement with the decrease of the energy gap with temperature. And the frequency can be increased or brought into the optical region by alloying the material with phosphor, which has a wider band gap. So tuning is possible here, which is generally not possible for other type of lasers. And some of the examples of semiconductor lasers are indium antimony, indium phosphide, gallium antimony, lead sulfide, etc. And their frequencies are extending from far infrared to ultraviolet region. So we finally understood that for the laser action to take place, population inversion is very important. So now let us understand which are the different methods of creating population inversion. So one option is the current injection method. Second one is the electron beam method. Third one is the optical method. So here in this energy level diagram, we can observe what actually happens with respect to the energy levels. It is just that in case of optical methods, we are making use of photons which are absorbed by the electrons, and these electrons will be excited to the higher energy state and finally get de-excited, emitting photon itself. But in case of electron beam method or current injection method, we can say high speed electrons are used which are responsible for the population inversion. So that is only based on the type of stimulus, and whatever is the requirement, based on that the method of creating population inversion for laser action can be chosen. But one thing to remember is the direct band gap semiconductors are going to show the population inversion, that is the laser action. So generally silicon and germanium, which are indirect band gap semiconductors, are not preferred because they don't show the lasing action, because there is a requirement of a phonon for assisting the excitation. So phonon is involved means again lattice vibration, which is going to create some heat in the system. So these are the methods, and the type of semiconductor which is going to be preferable is the direct band gap semiconductor itself. So gallium arsenide is one of the option for it. So by keeping all these things in mind, let us move on to the advantages and disadvantages of semiconductor lasers. So mainly the semiconductor lasers are small in size, simple, thus can be mass manufactured, as well as they are readily connected to the electronic circuits. They also have a high efficiency, and very important, which is not possible in others, is these can be easily tuned, that is by continuously changing the energy gap. So pressure etc. can be made use here. So as per the applications, tuning can be done. So small size means miniaturization, which is always going to be better option. Structure is simple means manufacturing cost is going to be reduced. Highly efficient, so we can rely on it. When we move on to the power consumption, that is also going to be very less compared to other type of lasers. So that is mainly the use of semiconductor which has changed the total era. Moving to the disadvantages. So here there is a relatively poor monochromaticity because the transitions are between the bands and not sharp atomic levels. That is the reason for that. And also there will be line broadening taking place, due to which we can say there is a poor quality of beam collimation. So in general we can understand there are some disadvantages, but the advantages are more over it. So however, to reduce the disadvantages, some of the steps also can be taken which is going to improvise the quality of semiconductor laser. And finally, moving to the applications. We know that in our daily life, everywhere we can observe the semiconductors, semiconductor devices, and also we make use of all these devices to the fullest. So for higher order applications, in general we can say display and IR illumination, pumping sources, medical and cosmetics, as well as surface treatment. So here we need high power semiconductor laser. But if we move for the general one, first one is optical fiber communication, next is the data readers, that is barcode readers or the disk readers, next is the scientific research, anywhere it is going to be useful to its best. Moving to the laser pointers as well as directional lighting sources, decorative purposes, then laser printing and scanning. Also for the medical field, lasers are highly recommended and it is used also. Even if we want to find out the long distances, it may be with respect to the celestial objects, we make use of it, that is long distance measurements. Also in case of defense, and if we go on counting the applications, the list is going to be too long. So these are some of the very important and understandable applications of semiconductor lasers. So this is all about today's class, where we understood about the history, of semiconductor lasers, the conditions, the working, construction, some of the important points about the population inversion as well as pumping, making use of the schematic diagrams, that is band structure as well as energy level diagram. Finally moving to the advantages and disadvantages with very important applications. And finally, I hope this is going to be helpful for you. So stay tuned and let's discuss more about physics in our coming classes. So see you in our next class. Till that, thank you.